Right. Ready? So good morning all of you. Good morning, sir. The summary of the last lecture, we have discussed this construction of evolved sphere. So what is this evolved sphere conclusion? So in which direction we are getting the diffraction phenomena, and in which direction we are not getting the diffraction phenomena, we can observe very easily. So because we have drawn this evolved sphere in the reciprocal lattice, we have drawn this in the reciprocal lattice. Each reciprocal lattice represent a set of parallel planes of your direct lattice. So which direct lattice planes are getting Bragg reflected, which are not Bragg reflected? This will be explained by that evolved sphere. Okay, so take a fresh page and put the heading, next one, very important, geometrical structure factor. Okay, just we explained earlier in which direction we are getting a diffraction, in which direction we are not getting diffraction. But you didn't explain now which planes are getting diffracted and which planes are not getting this diffraction. Okay, so that's why take a fresh page and put the heading, geometrical structure factor. Geometrical structure factor. So what is this geometrical structure factor? Ready? Very important, listen carefully please. So from the evolved sphere construction, from evolved sphere, we got a conclusion. What is that? All planes are not Bragg reflected, means no diffraction occurs in a particular direction, are not Bragg reflected, So how to know which planes are getting reflection and which planes are not getting? So that is the study now. So how to know which planes are getting diffraction phenomena or a reflection, whatever, Bragg reflection, diffraction. So the simple thing, for example, there exists a diffraction or there exists a reflection. So how do you know there exists a reflection? For example, forget about the crystal. Let us talk about the common sense light. Now here I have a plane. Now this is the light falling on the surface. Now I am getting some reflection. How do you check there exists a reflection? I will take the reflected wave and I will find the intensity. If I get the intensity non-zero, what I will say? Reflection occurs. If I get intensity 0, what I will say? No reflection. Because we can't see now. Have you seen the light ray is going like this? No, no. So how do you find whether there exists a reflection or not? By finding the intensity. The intensity of the electromagnetic wave is directly proportional to square of the amplitude. What is that? So here in this entire discussion we are going to find what is the scattering amplitude. Once you got the scattering amplitude, and I will find the intensity, which is the modulus square of the amplitude. If it is a non-zero, there exists a diffraction. If it is a 0, no diffraction. Point is clear? Right. So how to know which planes are getting a diffraction? For this, we are introducing this factor called geometrical structure factor. Before going to start this, let us introduce total atomic scattering amplitude. Just now I said I will find this because this will decide whether there exists a diffraction or not. Total atomic scattering amplitude. I hope you are observing, very important. This is represented by F amplitude HKL. FHKL. This is what we have to find. It's a simply amplitude. You can take a modulus later, not now, just leave it. Ready? Okay, what is this FHKL? Ready. So the FHKL is defined as everyone. So this is the total. For example, this is the unit cell. Let us say now let us suppose this is a unit cell, simple cubic or BCC or FCC. Let us suppose simple cubic. How many atoms are here in the unit cell? 8. Total how many are there? 8. But you need not to study the total 8. The number of lattice points per unit cell is what? 1. So we will take that atom. Is that clear? If you take a BCC, how many atoms will be there lattice point per unit cell? 2. And FCC 4. So here the meaning of a total atomic scattering factor means what? You have to take that amplitude for all the atoms per unit cell. You need not to study the entire crystal. I told you already. We are not going to bother about the 10 to the power of 23 atoms in the crystal. We are just bothering about only those atoms which are in the unit cell. I hope everybody understand. That's why here I am using the word total. So summation over J, that means summation over all the atoms. This is the represent atoms in a unit cell. So here we have Fj, I will tell you what is this Fj, small fj, into e raised to I phi j. E raised to I phi j. That's it. What is that j? Jth atom. That's what I said. It is a summation over atoms in a unit cell. Then what is this Fj? Fj stands for this is the atomic, means each atom, atomic scattering factor. Atomic scattering factor. And this phi j is nothing but the phase of that atom. Phase. What is that? Phase. That's it. This is the total scattering amplitude of the lattice or unit cell. Unit cell. You need not to talk about the entire lattice. Just talk about only unit cell. That is the summation over j. Fj, where Fj is. If I take a Brillouin lattice, what is the meaning of a Brillouin lattice? All atoms are, you are not studying the book. I said in the notebook, Brillouin lattice, all atoms are equivalent. All lattice points are equivalent. That means we are having at each and every point we have a similar atom. Okay. If you have same atom, this Fj is the same for all atoms or not? Shall I bring it outside? For Brillouin lattice, that means identical atoms. So the all atoms are having the same Fj. That's why F HKL equal to, I can bring it outside. You can write Fj or F, no issue. Summation over J, keep it as it is. E raised to I, because still here it is a phi j. Is it okay? That's good. And now let us focus on this. What is this? Up to this, no doubt, I hope. So what is this? A phi j phase. This is defined as phi j, that is the phase of the jth atom is defined as Rj bar. That is a position vector of that j atom, dot S cap by lambda minus S naught cap by lambda. I think everybody know what is this reciprocal lattice. Rj bar dot G bar. Cool. Okay. So in the textbook they have written direct answer. Here I am explaining separately. That's it. So ready. Everybody know what is R bar? That is the position lattice. Real space translation vector. Come on. And you know what is the reciprocal lattice vector corresponding to HKL plane. Corresponding to HKL plane. Good. And we know the relation between AB, that is AI bar dot BJ bar equal to 2 pi. If you are not focusing, you will lose the interview. Please listen carefully. So if you make the dot product, I hope you have already done earlier, Rj dot GHKL equal to 2 pi N1 H plus N2 K plus N3 L. Say yes or no? Now I can take this and substitute here. So finally, FHKL equal to F summation over J e raised to if you observe carefully, here we are having two things. One is N1, N2, N3, which is the direct lattice atom location, and HKL are the planes what you are talking. Which planes are getting refracted, which planes are not getting diffracted. That will be studied from this relation. Everybody understand? Come on. This is the amplitude, scattering amplitude. E raised to 2 pi I, that phi j just now we defined, N1H plus N2K plus N3L. This is what we get. And the geometrical structure factor, here I am writing FHKL by F, just bring this F this side. This ratio is nothing but the geometrical structure factor. Ratio of, here I am writing, total scattering amplitude to the atomic scattering factor is called GSF, which is equal to e raised to I phi j, of course a summation. That's it. Ratio of that amplitude and that scattering factor is called geometrical structure factor, which is called GSF. That's it. phi is that phase 2 pi m, where m is integer. This is integer. This is 2 pi m, where m is integer. I hope you know this is called Lavey condition of a diffraction. No? Lava, no, lava, no. What is this? How do you know that pronunciation? Your teacher pronounced like that, that's why you know that. I think L-A-U-V-E something. L-A-U-E. That a dot product is integer. That's the condition. Okay, after this just take this ratio, that is FHKL by a small f, which is nothing but summation over j e raised to I phi j. This is the ratio of a total scattering amplitude to the atomic scattering factor, which is called a GSF. But for checking whether the diffraction occurs or not, what do you want to take? Amplitude. So that's why once again write scattering amplitude FHKL equal to small f summation over j e raised to I phi j. What is phi j? Come on, what is that phase factor? 2 pi m. M is integer. What is that integer? n1h plus n2k plus n3n. While I am explaining the evolved sphere also, I told you that is an integer, then only the diffraction occurs. Ready? Right. Stop. So this is the scattering amplitude. Once again I have just written. So why you are taking the scattering amplitude? Here you are going to check whether the reflection occurs or not. Bragg reflection. I told you what is the meaning of that Bragg reflection. So whether it occurs or not. If a Bragg reflection occurs, there exists intensity. That intensity is proportional to what? Square of the amplitude. That is what we are going to check here. So here my intention is to check the intensity. The intensity is directly proportional to FHKL mod square. The simple logic, if intensity which is equal to or proportional to or anything, okay. So equal to na proportional to? Proportional to. So this FHKL mod square is not equal to 0, then there exists Bragg reflection. Otherwise no. Otherwise no Bragg reflection. I hope everybody understand this, why we are taking this amplitude. Are you ready now? Now I am going to check the simple cubic structure. Everyone please listen. So whenever you have a simple cubic structure, which planes are getting Bragg reflection, which planes are not getting, that is what we are going to check. Are you ready? So first let me take the simple cubic structure. Now this is the simple cubic. So total here actually you have 8 atoms. You have 8 atoms, but ready. So the number of atoms per unit cell. The number of atoms per unit cell. Yes, come on, how much? So 8 into 1 by 8 equal to? So how many atoms are there in the unit cell? So do you need summation here? Because only one atom. Where is that atom? You have to take the location. Shall I take it as a 0, 0, 0? Yes. There is only one lattice atom, sorry, there is only one atom per unit cell. That atom I am taking a 0, 0, 0. Because that is the only one, that is the origin. If I have 2, one I will take the origin, another I will take somewhere else. If I have 4, one at the origin, remaining 3 are somewhere else. I hope you everybody understand. That's good. So location of that one atom, N1, N2, N3, direct lattice, how much? Okay. Now I am taking the scattering amplitude FHKL equal to F summation over J, just I am writing e raised to I 2 pi N1H plus N2K plus N3. Now please take this and substitute. Then F, ready? Yeah. Summation over, no summation is not required because there is only one atom. So e raised to I 2 pi into how much? Here how much you got? E raised to I 2 pi 0. This total value how much? 1. Into 1. This 1 depends on HKL or independent of HKL? Whatever may be the HKL value, this value, whatever may be HKL, this value is always equal to? That means this is for all HKL or only few HKLs? That's it. So finally, the scattering amplitude equal to how much? That's why the intensity is directly proportional to square, which is proportional to how much? Is it a 0 or a non-zero? So 0 or non-zero? Non-zero. That means there exists a Bragg reflection or not? That means which planes are getting a Bragg reflection? All HKL planes. All planes. HKL. I will tell you what planes exist. Whatever you wish, it won't exist. There will be an order. Okay, I will tell you what is that. All planes are Bragg reflected. Bragg reflected. In which cell? In which unit cell? Simple cubic. Is that clear? 1 0 0, 1 1 0, 1 2 3, 1 1 2, 2 1 1, something like that. All the planes are getting a Bragg reflection in simple cubic. Don't copy. Please try to write yourself. Do it yourself. Very simple, not difficult mathematics. Did you study evolved sphere? So any new point you find, any unknown point, any new point, what new point you find after the class asked? If you want to clear the interview, now only please read. Generally some people, stupids, they will think for interviews separately we will prepare. No, there is no separate preparation for interviews. The same subject, same subject. They won't ask biology questions, they will ask physics questions only. If you are having the habit of answering the questions in the class, you will answer in the interviews. Otherwise, you have to take separate coaching. Ready? Right. The next one, ready. Let me explain the next one. Simple cubic is over. Next one what? BCC. Are you listening? Yes, sir. Now let me take the BCC structure. You can also draw. BCC structure you can draw meanwhile. So here first we have to calculate the number of atoms per unit cell. Just calculate that also. Number of atoms per unit cell. So which is equal to 2. How it is? 8 into 1 by 8 plus 1. That's why it is 2. Ready? Stop. Okay, so the BCC structure, number of atoms per unit cell is 2. Now I have to take 2 atoms. So I am fixing the 1 atom at the origin. That's why 0, 0, 0. Another at the what? Body center. It's a body center. That means from all the side it is a halfway. That's why how much it is? 1 by 2, 1 by 2, 1 by 2. Is it clear? So what are these coordinates or location? Don't write, see the board. Locations. The first one is 0, 0, 0, and the second one is half, half. Halfway, that means in the middle. That's it. Now we have already defined FHKL equal to small f summation over j e raised to 2 pi I, come on, n1h plus Now ready? Now I have to expand this summation because here I have 2 atoms. Now this capital F I am writing HKL, this is the small f. Now I am removing the summation, first 0 0 0 0, that is why it is 1 plus e raised to, are you ready? Yeah, 2 pi I n1 n2 n3, half half half, half gets common, 2 gets cancelled, come on. So surprisingly, this final value definitely depends upon HKL. That's why I am taking 2 cases. Ready. Now I am taking H plus K plus L is even. H plus K plus L is even. Is it okay? I am taking option because this is the integer. H plus K plus L, some integer is what? I am taking even. Or I will take H plus K plus L is odd. If it is even, I hope everybody know, e raised to pi I, even number, this is always equal to, and e raised to pi I, odd number, this is always equal to. Now take this one and substitute, then capital F for HKL planes equal to F into 1 plus 1, how much? Now the intensity is proportional to how much? 0 or non-zero? That means for which planes H plus K plus L is and the sum is even. Any doubt? So once it is a -1, take it and substitute, then FHKL equal to F1 minus 1, how much? So intensity, is there any Bragg reflection? No. So which planes are Bragg reflected for BCC structure, for which H plus K plus L is, ready? I will say one plane, you please tell me whether the Bragg reflected or not. 1 2 3, triple 1, 2 2 1, no, yes kadani mundu 2 plus 2 plus ade inda cheppanu, some additions subtractions kuda marchipoyaru. 1 1 0, yes, sum is even, Bragg reflected, sum is odd, no. Don't copy, do it yourself. FCC, try yourself, and finally I will help you, don't get tension. After writing this FCC, do it yourself. Maybe if you didn't understand the locations, please wait for me, or if you know, do it yourself. So which planes are Bragg reflected in BCC? Only those for which H plus K plus L is even. FCC. Number of atoms per unit cell. Number of atoms per unit cell. I hope everybody know 4. How it is 8 into 1 by 8 plus 6 into 1 by 2. That's why 4. So total 4 atoms we have to, is it over? BCC completed. Ready. So total 4 atoms we have to give. Let me explain the location, after that you can do. So one of the atom you can take the origin. Then if you assume this is X, Y, Z. Total 4, one you have taken origin, because we have one atom for this 8, and all those 8 atoms are corresponding, are represented by 1. I hope that is the meaning. Next, after that, the 3 phase centers are there: XZ plane, XY plane, and YZ plane. Now if it is a XY plane in the middle, XY plane in the middle, good, half comma 0. YZ plane 0 comma half, good. XZ plane half comma 0 comma half. Are you ready? Start. Locations. So that is 0 comma 0 comma 0. XY plane half comma 0. XZ plane half comma 0 comma half. YZ plane 0 comma half. The total SSP notes. Where is SSP notebook? Oh, no, from that side. Those many papers when I explain. I think you are getting a total 4 terms. One term is 1. After that, e raised to pi I h plus k plus e raised to pi I k plus L plus e raised to pi I h plus L. Two terms. Because half, one, another is 0. So here you got FHKL equal to small f summation over j e raised to I 2 pi n1 h plus n2 k plus n3 L. Now I am removing this summation. First atom is 1, that means e power 0 1 plus Next half comma 0, that's why e raised to I pi h plus k, because half plus half hk, plus e raised to I, you can write it as okay, anything you can take k plus l plus, sorry, e raised to I pi, come on, e raised to I pi h plus l. Everybody got this? Right. Right. So now we have to check where we will get the intensity and where we won't get the intensity. Everyone stop. Okay. Now first one I am taking HKL. BCC we have taken H plus K plus L is even. Now HKL are unmixed. Unmixed. Wait. Unmixed. What is this unmixed, sir? See. Means take either even or all are odd. Either take all are even or either take all are but not mix. And both even and odd numbers should not be there. Either all are odd, 1 1 1 1. Either all are even, 2 2 2. 1 1 0. Odd, even, both are there. That is mixed. Is that clear? Good. So all are. That means all are even or odd, but not both. That's why if you see carefully, sum of any two integers, sum of any two integers. Here you are taking all are or all are. That means you will get sum of any two even or sum of. So even plus even is always even. Odd plus odd is always even. That's why anyhow in the both the cases you are getting what? Even. That's why e raised to I pi even number. How much? How much? Now FHKL equal to small f into 1 plus 1 plus 1. That's why intensity is a proportional to 16. Clear? And next come to this. I hope everybody understand. So which planes are reflected, Bragg reflected in FCC planes? H, K, L are unmixed. Either all are even or all are 100 plane. In FCC 100 plane get Bragg reflection or not? Why? 100. 200. Yes. 100 plane not Bragg reflected, but 200 plane is Bragg reflected. 110. No. 111. Ready. Next, here HKL are mixed. HKL are mixed. Mixed means I am taking both even numbers as well as odd number. We can't discuss like this more generally because those are mixed. Anything can be mixed. That's why how to take an example. Say anyone? 1 1 1 0. 1 1 0. Here all are mixed or not? Yes. That means your H is 1, K is 1, L is. That's why if you see carefully, H plus K equal to 2, H plus L equal to 1, K plus L equal to 1. So this is even, this is odd, and this is also odd. That's why, come on, FHKL equal to F into, first one is 1. H plus K even, that's why H plus L odd. Are you listening? K plus L, odd, how much? Acting. ఏంద్రిది how much? 0. For whom I am explaining? Idiot. So amplitude is 0. That's why intensity is 0. That's why no Bragg reflection. No Bragg reflection. That's it. So finally all the things you got: simple cubic, no restriction, all the planes are Bragg reflected. BCC restriction is there, H plus K plus L is even. Next here FCC, H, K, L are unmixed, either all are even, all అంటే ఏం లేదు 3నే, all 3 are even or all 3 are diamond. Diamond crystal, which planes are Bragg reflected, which planes are not Bragg reflected? Why? మీ బొంద. H plus K plus L is divided by 4. H plus K plus L is divided by 4. write somewhere note for diamond crystal cubic for diamond crystal cubic H plus K plus L is divided by 4. H plus K plus L is even. H plus K plus L is even and divided by 4. Divided by 4 means definitely even, sum is. Without sum even, how it will be divided by 4? Not possible. That's why I didn't give that. H plus K plus L is divided by 4 is enough. Odd number will be divided by 4. That's it. Divided by 4 is important condition because that is a combination of two FCC structures with 4 atoms on the diagonal. Over. Right. Right, ready, stop. So here we have to give the tabular form. So which planes are first Bragg reflected, which planes are second Bragg reflected. In the question, sometimes while you are solving the problems, he will say the interplanar separation for those planes which are second Bragg reflected, which are first Bragg reflected. That means they won't mention the HKL value. They will say indirectly that HKL stands for first Bragg reflection plane, second Bragg reflection plane, like that. So you have to know which are first, which are second, which are third. For that I am going to give a tabular form. Everybody, ready? Stop. Planes. So here you have to take the planes, that is HKL planes. And wait a minute. How we will write these planes? I will tell a small technique. 1, 0, 0. What is the magnitude? 1, root 1. So increasing order of the magnitude, root 1. The next one is a root 2. Okay. So that means what? 1. Come on. 1, 1, 0. Next root 3. Okay. Like that you have to remember. Only this is the order of the planes. Whatever the plane you want, it won't be there. Actually for that also some mathematics is there, but we are not discussing those things because of time restriction. So root 3. Next root 4, 2, 0, 0. Next root 5, root 6. Correct. 2, root 6, root 7. Not possible. Root 7, sum of squares of 3 integers never be equal to 7. That's why 7 not possible. 8, 9. So this is the way how to remember the order of the planes. Okay, root 5 and root 6 and root 8 and root 9. Okay, cool. So after that I am taking the simple cubic and next BCC, simple cubic, and next BCC and next EFCC. Ready? So simple cubic, any restriction? All values. All values are Bragg reflected. Now what is the first Bragg reflected plane in simple cubic? Second also must remember. Minimum 3 planes you must remember. First, second, third you must remember. You forgot. Take the numbers like this. It's very simple. For BCC, H plus K plus L is Just add and check whether it is even or odd. Is it even? Is it even? Is it even? Is it even? Next. 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 For BCC, what is the first Bragg reflected plane? Second Bragg reflected plane. So you must remember this. They won't mention, you have to remember. And FCC, that means HKL, unmixed. And either you have all or even, or either you have all or. Is it all or even or odd? Mixed or unmixed? Mixed. Very few people are saying. Next. First Bragg reflected plane in FCC. Second Bragg reflection plane in FCC. 200 is in all it is Bragg reflected. Similarly 220, 200, 220, something like that. Is that clear? Right. the ratio of h plus k plus l square, h square plus k square plus l square for Bragg reflection in simple cubic 1:2:3:4:5 so on, and for BCC 2:4:6 so on, and AFCC 3:4:8 so on. Ready? Right, that's it. So this is the end of this crystal structures, reciprocal lattice, XRD, evolved sphere, and after that atomic scattering amplitude. From this we can say which planes are Bragg reflected or not. Now check a fresh page and put the heading lattice vibrations, the next topic. Lattice vibrations. This is a very important. And now onwards, from this crystal structures you will get one question. Lattice vibrations, one questions. And a band theory of solids and a free electron theory of metals, and what is that? Magnetism, superconductivity, and after that a Hall effect. These are the topics actually. So listen. Lattice vibrations. So why we are studying this lattice vibrations? Now, ready? Are you ready? Now, first of all, what is meant by lattice? Already we have defined, it's an array of, am I right, atoms. It's a regular arrangement of atoms. Say yes or no? Now for example, SAR is not there. Let us suppose you are all at lattice points. That means you are all atoms. SAR is not there. Okay. Somebody enter into the classroom. Then what you will do? One person seen. Some boy seen. And after that what happened? Some special is there, that's why he observed. Then what he will do? Then what that person will do? What another person will do? Like that. So that means what will happen? Everybody will turn like this. Say yes or no? So that means what? The motion of one atom is shared by all the atoms. That means in a lattice, all the atoms are coupled. All the atoms are coupled. The one disturbance created, a disturbance created at one lattice point is carried throughout the lattice. Is carried throughout the lattice. That's why these vibrations are called lattice vibrations. Sir, how that one lattice point will be disturbed? Maybe mechanical force, maybe electromagnetic force. Electromagnetic force means you are sending X-rays, you are sending some other. Okay, fine. Wait a minute. So the lattice means a regular arrangement of atom. Here what I am saying is, the lattice is a combination of atoms. but the atoms are coupled. The atoms are coupled. What is the meaning of a coupled? That means the motion of, very important, the motion of, after this Debye theory, Einstein theory, everything will come from this only. Please listen carefully. The motion of one atom is shared by all other atoms. All other atoms. That's it. That's why we can say the motion of atoms are coupled. That means atoms are coupled means motion of atoms are coupled. Okay, that's it. And ready. So here we are getting lattice vibrations. How you are getting lattice vibrations? First of all, that means what is meant by lattice vibrations? A disturbance created at one lattice point is carried throughout the lattice. I am not giving those definitions, so I hope you understand. But what is the reason for that? This is a good thing. The lattice vibrations due to, if you want, you will, I will write this, disturbance at one lattice point is carried throughout the lattice. What is the reason for this? Means the atoms are coupled. That's why it is carried. Okay. What is the reason for this lattice vibrations? There exist two reasons. One is internal energy. Internal energy. Internal energy means no one came into the class, but student is not interested. What he will do? That is internal energy. Himself he disturbed. That's why. So by seeing that fellow, another fellow also will do like this. So finally, this is the internal energy. And no external force is there, only internal energy. Okay. So this is due to internal energy. Okay. Right. So with this internal energy, we will get the lattice vibrations, and this is useful. This is useful to study the properties of specific heats. While you are studying the specific heats, you will take the internal energy, not that one, external force. Be careful. Specific heat and thermal conductivity. This is some rule is there. Just wait, I forgot the name. Thermal conductivity. Lorentz-Drude model, or simply Drude model. Specific heat and thermal conductivity or thermal conduction. That's it. So here you have U lattice. U lattice is due to internal energy. This is the internal energy. This is useful to study the properties of specific heat as well as thermal conductivity if you want. And here specific heat we have Einstein model, Debye model, Dulong-Petit model. Dulong-Petit, that is the classical. Next one quantum, Einstein and Debye. Which is correct? Debye. That's it. Now ready. So next one is due to external force. External force. The external force is given by two ways, either electromagnetic wave, which you are sending just like X-rays, or mechanical wave. Mechanical wave. Some collisions or something like that. That is a mechanical wave. What is the meaning of mechanical wave? I didn't ask the example of mechanical wave. What is mechanical wave, I ask. If a 10th class student asks what is a mechanical wave, Anna, you will say sound wave. What you will say? A wave which needs medium for the transmission is called mechanical wave. That's why sound is a mechanical wave. Ready? EM wave or and here this is used to study the properties optical and acoustic, optical and acoustic, properties like optical and acoustic. That's it. So finally, this is your, what is the reason for the existence of lattice vibrations means one is due to internal energy, another is due to external force. Is it clear? First come on, write down. So, okay, we can't see what is happening inside the lattice or inside the solid. That's why we need to prepare a model. So, first we let us go with the one dimensional model first. That too again two types are there. One is the discrete, another is the continuous. Very important, listen carefully, very crucial. Why today's so much problem? That's why. Right, ready. Must stop. Ready. So here we have to know what is happening inside the lattice, how the atoms are oscillating, how the atoms are vibrating, but unfortunately we can't see inside what is happening there. That's why let us go with the models. Okay. Now I am taking a one dimensional model. That too what I am taking first one, 1D monoatomic model. That means I have only one atom. Just like a sodium, 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 like that, one atom only. Okay, right. So this model is also called as discrete nature. Which nature? Discrete nature. Don't forget this word. This plays a very important role here. Now which model we are taking means which model we are taking? Discrete. Now here I am considering a 1D chain, 1D a linear chain, linear antene 1D, linear chain of n atoms of each mass m. That means you have taken same atoms. That's why it is a discrete. Is it clear? Now, I am taking like this. Everyone, please listen. This is the nth location. This is n plus 1. Sorry. Coupled. This indicates coupled. There is no spring. Okay. That indicates what? A coupled. And so on. And here you have n minus 1th site and coupled to n, and this is the n minus 2 site coupled to n minus 1, so on, something like this. So this is the 1D lattice where you are having a m, small m, at each lattice point, small m, at each lattice point. I request you please read the book after the class. Don't neglect. Boys are not studying. Again you are going back. So that also will go back from you. And here I am taking a nth atom. That's why first let me take only one atom. What is that? Nth atom. Ready? Yeah. If I take the lattice spacing is A like that, somewhere I have the origin. Could you please tell me what is the distance of this nth atom? All are AA spacing, then nth atom spacing x equal to. All these things, sentences will be in the textbook. Is that clear? Right? I have taken nth atom, which is coupled to n minus 1, and similarly which is coupled to this n minus 1, and here it is n plus 1. Ready, Amma? So this is m, and here also m, and here also m. Go back to classical mechanics. What we have taken? Equilibrium positions. So this is the equilibrium position. Now I am taking, this is the displacement un. This displacement un plus 1. This displacement un minus 1. Default we have to take. In which direction we don't know. That's why we have to take like this. And I am taking stiffness is beta. Beta. Something beta. Ready. So how much? un plus 1 minus un. Come on. So now we are going to find the net force acting on this nth atom. Say yes or no? We are writing for the nth atom. Okay, so we know one thing, restoring force. If I say specially restoring force, I need not to take that minus sign, because the restoring force means what? Opposite to the displacement. If I consider displacement forward, my restoring force will be backward. That's why I am not using any negative sign. That negative sign purely indicates what? A restore. But here I am writing. Is it okay? Wait. Otherwise there will be some sign difference. That's why I am taking like this. Otherwise some teachers will explain like this. Just wait. Just see. Restoring. F restoring force is directly proportional to net displacement. Come on, say un plus 1 minus un minus plus difference amma un. Good. Some people will take minus, but they will take this one first, that one second. But here I have taken this one first because the right side. Okay, just I have taken like that. It's not a wrong thing. No need to get tension. Restoring, not rest. Restoring is proportional to, simplify, un plus 1 plus un minus 1 minus 2 un. I am removing this proportionality constant. The restoring force is equal to beta stiffness un plus 1 plus un minus 1 minus 2n. So definitely what is this? It is making SHM. Say yes or no? Yeah, it's making SHM. Okay, right. That's why the restoring force is directly proportional to the displacement. Finally, I got this. Everybody understand? Now this nth atom is making SHM. For SHM, everybody know the solution. Solution means what you are finding, x value. Here x is nothing but what? Un and displacement. This un equal to some amplitude. What? un naught you want to take a తీసుకుందాం. Some a e raised to I omega t plus kx. Anything you can take. A e raised to I minus kx or plus kx, anything you can take. No issue, don't worry. I already told you which atom it is. Which atom? For nth atom, what is the distance? What is the distance? Come on. Then un equal to a e raised to is it okay? Now, from all these things, I am going to write un plus 1. Ready? Amma, this nth atom is making SHM. That's why this is the solution of SHM. Everybody know this is the sinusoidal. And x is the distance of that nth atom, which is Na. That's what I have done. Now I am finding un plus 1. Same solution, but x is equal to, ready, start. E raised to I omega t plus k n plus 1 into, sir, why you have taken same amplitude, same atom? If I have two atoms, I cannot take same amplitude. Understand? So simply this can be written as a e raised to I into e raised to I ka. Is it okay? E raised to I ka into. Similarly, could you please tell me un minus 1? Everybody understand? Small algebra, not at all difficult. Now, once I got all these three things, now I will take it and substitute. Come on, do it. Please read the book, don't neglect. Today itself read the lattice vibrations. Immediately study and go. No need to bother about the signs. I have taken displacement forward, then definitely my restoring force is backward. Then you will get automatically minus sign, then no need to bother about those things. Slowly, not at all difficult. Lattice parameter is A, that's why nth atom distance from the origin is Na, and out of that chain we have taken the nth atom for the SHM, and displacements we represented. After that we have written the Hooke's law, that's it. Beta is the stiffness, force per unit length, and after that SHM solution everybody know, that's a sinusoidal. For first I have written for nth atom, and by using that I have written for the remaining atoms. If anybody got why SAR is taken same amplitude, because the same atom, that's why it will vibrate with the same amplitude. Don't simply copy, you won't get interest while you are revising. Do it yourself, do it yourself. So the restoring force we have taken beta un plus 1 plus un minus 1 minus 2un. Already you got what are these un and un plus 1. Un is the solution of that SHM equation, and un plus 1 you got e raised to I ka into un, and un minus 1 equal to e raised to minus I ka into un. Sir, why you are deriving this? If I say this 1D monoatomic lattice is a low pass filter, just I said this statement and I left. How do you understand it is a 1D or low pass filter? It's a low pass filter. That lattice acts like a low pass filter. What is the meaning of low pass filter? Which allows lower frequencies below a certain maximum frequency. Beyond that it won't allow. So how do you know means you have to do the derivations. In UV they will do all the derivations, means we will do the derivations to understand one small sentence. We can't give the sentences and leave. You have to know. Ready? Yesterday I am watching some people, some institutes nowadays they are placing the videos also, class videos. We are not placing, just I am watching what is the difference between them and me, whether I am bad or good, I am just watching. Okay, I won't comment on those things, they are also good, they are professors. Some person is writing like this, the wave function of spin alpha 1, beta 1, alpha 2, beta 2. And 3 electrons he has written like this. Under that comments, super, very good, nice, excellent. But Bonda, wrong. Why wrong? Determinant 0 na? సో ఏ మాత్రం కామన్ సెన్స్ లేకుండా జస్ట్ దే విల్ రైట్ లైక్ దట్. అది వాడి సరే ఆయన కామన్ సెన్స్ లేదు, ఈయనేవాడికి ఉండాలిగా కామన్ సెన్సు. మళ్ళీ పైగా ఒక కామెంట్, వెరీ గుడ్ సార్, సూపర్. ఏంట్రా సూపర్, నీకు బాగుంది సూపర్. ఏంటో నో నార్మలైజేషన్ కాన్స్టెంట్, నథింగ్. అది క్వాంటమ్ మెకానిక్స్ కాదు, అదేంటది, అదేదో క్వాంటమేగా. ఏమైందంటే బికాస్ ఆఫ్ దిస్ కోవిడ్ ఎవ్రీబడి స్టార్టెడ్ ఆన్లైన్ క్లాసెస్ నా లైక్ దట్. Ready? I will also write some mistakes sometimes, overlooking. I am not saying I won't do mistakes. But next day I will correct. If I find any mistake, next day definitely I will correct. Ready? Are you ready? So this is the SHM equation. We got the SHM. That means they are all, vibrating about their mean position. And this is the net force acting on the nth atom. This is what we get. Everyone see the board. So now I am taking this and substituting. So this F equal to beta un plus 1. Come on, say. Come on. Now with your permission, I will take un common. Shall I? Then what is the remaining? Super. Now with your permission, I will write like this. But something is missing. A square ready. So, say sir, no? Right. E raised to I k a by 2 minus e raised to minus I k a by 2 whole square. That means a square plus b square minus 2ab. Still some factor is missing by 2i whole square into minus 4. Is it okay? I think minus 4 you didn't understand, I hope. So this is beta un. This is the force. Good. Amma, any doubt? A square plus b square minus 2ab, amma. I want to write it as a sign. That's why I have written by 2i whole square into 2i whole square. This is nothing but minus 4 beta un. Come on, I say. That's good. And this is nothing but force. Huh? Ready. So what is this force? Force is nothing but, any force is nothing but F equal to ma. Where A is what? Acceleration. That's why this d square displacement differentiation by dt square. Say yes or no? Because this is nth atom. Now everybody know un equal to some amplitude e raised to omega t plus kx. Then d square un by dt square. 2 times derivative. 1 time derivative I omega, another time derivative I omega, finally. So this is nothing but minus m omega square un. Now un minus gets finally m omega square equal to 4 beta sine square. Finally omega square equal to 4 beta by m sine square ka by 2. So omega equal to plus or minus under root sine ka. Is it right? Only plus. Frequencies never be negative. Never be negative. That's why omega equal to under root. Is it correct? Think. Because the sine Ka by 2 may be negative. That's why in the books they will write the magnitude for this. The reason is omega is always positive. That's it. And this is what? The great dispersion relation. The dispersion relation for 1D lattice. Which lattice? Discrete or continuous? 1D discrete. Come on. Small algebra, no need to copy, do it yourself. A plus A minus B whole square, nothing else. I hope some of you understand what we are going to discuss here. Acoustic branch and optical branches. How we are getting those branches we are discussing. This is the 1D monoatomic lattice. That's why it is a discrete in nature. Finally, here we got the dispersion relation under root 4 beta by m into sine Ka by 2, but this is also a modulus. Ready? Now stop. Over. Right. So this is the dispersion relation we got. Everyone please listen. Stop writing. Here we have to introduce one thing called elasticity. Elasticity. Generally this is called modulus of elasticity, E. This is having a three types: Young's modulus, rigidity modulus, bulk modulus. Young's modulus will talk about linear, and rigidity modulus will talk about area, surface, and bulk modulus will talk about what are these things means. This will give you velocity of sound in the material. Velocity of sound in the material. For example, if it is having a linear strain means like this. Okay, surface strain means area, volumetric strain. Is that clear? So for example, it is having a linear strain. That means what it is having? Young's modulus. So under root Young's modulus by density is nothing but the velocity of sound in this. Understand? Under root B by density is nothing but velocity of sound. That B stands for rigidity modulus. Bulk YK anyhow whatever it is already. So that is the modulus, right? Listen, Modulus, stop, amma edo okati amma. Modulus of elasticity. What is the definition of this modulus of elasticity? Ready. This is called a stiffness. But here we are talking about 1D. That's why it is called linear stiffness. So the linear stiffness is defined as E equal to, the linear stiffness is defined as beta into A, where A is what? Lattice parameter. That stiffness constant is what? Beta, the force constant. From this we know what is a beta. Beta equal to how much? And one more thing, density. Density is nothing but the mass per volume. That's why a mass by a volume. Say yes or no? But here it is a linear. That's why mass per length. How much? A. So don't take volume because it is a linear. Mass per length. Is it okay? And that implies I can write m equal to how much? Now ready. By using those quantities, omega equal to under root 4 into beta, m, rho, that's good, into, but don't forget that is a modulus. This is 4 out, 2, a square out, a under root. This is what I said earlier. Under root modulus by density is always velocity of sound. Adi Young's modulus, rigidity modulus or bulk modulus, whatever it is. So this is into sine k. So this is nothing but velocity of sound in the solid. Velocity of sound in the solid. That's good. So finally my omega can be written as 2 Vs by A sine Ka by 2. Anything you can use, either this or this. Everybody understand? Right. Now see the board. Now we are taking the first case, case 1. What is this first case? Lower frequencies. Lower frequencies. That means I am sending the electromagnetic wave through this 1D lattice. There is a 1D lattice. I am sending an electromagnetic wave which is having a very low frequency. Low frequency means what? Higher wavelength, larger wavelength. Say yes or no? Are you listening? Yes, sir. Higher wavelength or larger wavelength. Under this limit, what will happen? If wavelength is large, I hope everybody know, k tends to 0. K tends to 0 means lambda tends to what? Infinity. I hope you remember, if theta is small, sin theta is nearly equal to, you got a doubt. Sir, theta is small, some people will say take 0 because sin 0 is 0. Some people will take sin theta equal to theta. Why you have taken sin theta equal to theta? Why you are not taking sin theta equal to 0? Remember, in lattice vibrations, wherever you are taking the approximations, take any approximation, either first, either first, second or third, anything, but omega should not be 0. Like that you have to take. First suppose, if I take theta 0, sin theta 0. Yeah, for very very small angle, sin value is what? 0. But if I take 0, my frequency become. That's why I should not take that approximation. I have to go for the next approximation. So sin theta is nearly equal to. That's why sin Ka by 2 is nearly equal to everyone. Omega equal to, come on I say, 2 Vs by A sin theta, AA, 2, answer, Vsk. Ready? Now, once you got omega, from quantum mechanics, we can find phase velocity. Omega by omega by k. How much? Next you can find a group velocity. Group velocity. Vg equal to how much? Group velocity equal to any dispersion? No dispersion. Sir, what, sir? What is dispersion, sir? Wait. Now here I have light in air medium. I want to study the properties of light. What you will do? You will study in the air like this. Yes, say. No. What you will do? You will take a glass, you will take a prism, something you will keep it. Am I right? In that material, if the light get dispersed, then only you will study the properties. For suppose, I kept a material, a solid, just what I have, listen, conclusion listen, mathematics everybody understand. So conclusion listen. Here I have taken a 1D linear chain which is a discrete in nature and I kept the lattice before this electromagnetic wave. Now finally what we get? There is no dispersion. If there is no dispersion means it is not interacting with anything, means there is no change in the group and phase velocities. So that means what? There is no dispersion means will you get any properties of this material? No. Or properties of EM wave, whatever it is, vice versa, anything. So will you get any properties? No. Is it useful? No. Now tell me, at lower frequencies, 1D atomic, 1D linear discrete nature. 1D and linear nokate. 1D discrete nature is useful or not? No. Why? There is no dispersion. If dispersion occurs, if some change occurs, then we will see, oh, this change is due to what above, why it happens, what is the reason, then we will know the properties. Then we will know the properties. Tomorrow onwards, don't attend the classes, get lost. నువ్వు ఇక్కడే ఉన్నావు అంటే మళ్ళీ చెప్పు తీసుకుని ఇసిరేయాల్సి వచ్చింది నీ మీద, పో వెళ్ళిపో. మేము ఇంతే, మా ఇన్స్టిట్యూట్లో ఇంతే. ఆ గాడిద కొడుకు చెప్పడం కంటే వేస్ట్ అసలు, ఆడంత దరిద్రుడు ఇంకోడు ఉండడు. నిజంగా గాడిదే. ఎందుకు? ఈ పేరెంట్ పెయిడ్ 65,000 60,000 పెయిడ్. అవునా? ఏ మాత్రం రెస్పాన్సిబిలిటీ లేదు. నాయసరం నీకేందమ్మా, నీకు డబ్బులు వచ్చినాయి కదా. నాకు నచ్చదు. ఐఎమ్ నాట్ ఏ ఈడియట్ లైక్ అదర్స్. I don't like. Ante. Instantaneously we will send them out. Although they are sleeping, if we are teaching, we are waste fellows. I think still in India, some ethics are there still. I hope so. Ready? Are you ready? Ready. So what I am saying is, here you have taken the lower frequencies EM wave you are sending and you want to study the properties of this lattice. But unfortunately what happened, whatever the lattice you have taken, that is a discrete in nature. That discrete nature of lattice, this is very important. The discrete nature of the lattice is not important for lower frequency waves. Means no use. That's why we are not using this lattice for lower frequencies. But higher frequencies, what will happen, we will discuss later. I hope everybody understand what is the meaning of dispersion, no dispersion. Hence, what is the conclusion? The discrete nature of the lattice is not important for, write down. Here not useful means we won't get any information. Why we won't get information? No dispersion. See earlier why we are discussing the light to prism experiment, there exists a dispersion and then we get the properties of that. So here we won't get any properties, that's why some people will say discrete nature of lattice is not sensitive, that is the good word, textbook word I think, not sensitive. Not sensitive for lower frequencies. It's a very, 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 very important conclusion. But if I take higher frequencies, I cannot neglect Ka by 2. So what I will get? Phase velocity is one thing, group velocity is a differentiation, cos. Sine and cos both are different. That's why for higher frequencies, your discrete nature of lattice is responsive. That means it will respond to higher frequencies, but it won't respond to lower frequencies. That we will see in the later, and what is the branch we will get, we will see. Only case 1 completed. If you are interested, just read that case 2 also and come to the class tomorrow. There exists only one branch, that is acoustic branch, where you will get optical branch also, continuous nature. That means tomorrow we will take the 2 atoms, one is a capital M, another is a small m. That indicates continuous nature of 1D lattice. In that we will get 2 branches, optical as well as acoustic. Please read the book, otherwise so no use. It will be very useful for interviews, please read. Not simply reading, read and write the points also. SSP no problem, it will be complete within time, only fear about electronics. How to cover. Online no problem, offline they are not having any exam now. I mean they are not, we are not having any exam. You will go home, they are already at home now, no problem. So the final conclusion is we have taken a discrete structure, that is only monoatomic lattice, that indicates the discrete nature. Unfortunately, our lattice is not responding, that means it is not sensitive for the lower frequencies. Tomorrow we will understand why we are studying this lattice vibrations and what is the need of that. Tomorrow you will understand. Over.